Is everybody with me?
Mm-hmm.
Yeah.
So there's no way to decide what the total order is until they actually touch down, because when they're racing, you can't identify what variable across the network is telling which one to touch down first.
There wouldn't be any way to tell that order that we might call arrival order, right? So if we have just one machine, we can use arrival order as our oracle. Arrival order is the order, and you're right, we couldn't know that ahead of time. But arrival order isn't the only order we could have used, right? We could have, as we said, these clients could have all asked Ophelia the oracle, yo, can I have a chip? Can I have a number? And she's like, yeah, you're 27. Okay, cool. Hey, can I have a number? Sure, you're 28. And then it's like, okay, that's the order that Ophelia told us the numbers in. And then we did know the order afterwards. It's just, it cost us an awful lot to do that communication, and Ophelia could go down and all this kind of stuff, right?
It seems like it would be accomplishing the same thing as just the arrival order, because the arrival order as Ophelia is the number again.
All right, yeah, I mean, we would never do this unless it was more than one D. But if there's more than one D, then Ophelia, arrival order doesn't work anymore, and you need something else, right? Yes?
Yeah, so to relate to that point that she was making, I think that the interesting question here is, what if you ran this whole thing more than once, and you wanted those two runs?
Oh.
So that is a question of determinism.
I was just about to ask about determinism. Thank you.
Yeah, so, I mean, well, I mean, maybe it's a little bit of a sidebar, but why would it be nice to get the same result if you ran the same algorithm more than once? First, let me say, you don't need determinism to make replication strongly consistent, you just need a total order. But if you had determinism, replication would be pretty easy, right? Like if I knew the replicas were going to get to the same state no matter what order they got their messages, I've already won, right? But why would you want determinism beyond knowing that your replicas are going to get to the same place? Why is it a nice property to have in the system? Why would I pay even more to get determinism?
Debuggy.
You want to expand on that a little?
Oh.
Anybody have a sense of why determinism will be helpful in debugging? Anybody ever try to debug a distributed system? Yeah.
I haven't, but if you have a test and you run it 10 times and 9 times it does one thing, 1 time it does another thing.
That sucks. Yeah. Yeah. So I mean, the way that I learned how to debug back in the good old days was you keep rerunning the program and changing it until the assertion error goes away. Yeah, that's still a bug. Still a bug. That didn't work. That didn't work. Oh, there we go. Now it works. And then you go home or whatever. But if sometimes it works, sometimes it doesn't. That sucks, right? So you might be willing to pay a little bit of an instrumentation cost to be able to go back and get some kind of guarantee that a system will produce the same outcome and take the same steps over and over again. It's easier said than done. Deterministic debugging in distributed systems. Yeah?
You can just use the loop to keep trying to reconnect if you disconnect.
What do you mean? Like if you were doing replay-based debugging, or
Or say one of your servers goes down, and you just keep trying to reconnect.
I mean, I think that's more of a general question about what do you do in the face of partial failure. And I think that in practice, what you do, this isn't really so much related to the subject of deterministic debugging, but what you do is you keep trying to reconnect some reasonable number of times, after which you say, if I've tried 10 times and that guy's not down, I'm going to get on with not up, I'm going to get on with my life. So typically, what's called bounded retry. Maybe you play tricks like, we'll talk about this a little bit more when we get into consensus, but maybe you say, you don't just keep retrying after every 5 seconds, you kind of start doing exponential back off, where you're like, I retry every 500 milliseconds, and then if I haven't heard back for a while, I try a second, and then I try 2 seconds, 4 seconds, 8 seconds, trying less and less frequently, so that I don't overwhelm the network. Yeah?
If you were going to debug a threaded program on a single machine, you consider every possible permutation of the instructions on each thread running, every possible permutations of those instructions running. So what if you, instead of debugging deterministically like this, you just take every message that was sent and permute them like that's n message factorial number of permutations, and then consider every possible outcome?
Yeah, it's worse than that though, because it's one of the things that's it's worse than that. It's is it worse than exponential? Well, it's really exponential, right? Because in some sense, can I do this? Let's see. It's the number of things is the sum of all. No, I can't write this summation. But basically, there's 2 things interacting. There's the power set of the messages, right? So there's 2 to the n, if I send n messages, how many patterns of message sending are there? Well, there's the power set event, because messages can be lost, right? So if I send messages A, B, and C in some execution, there's this other execution where I just sent A and C, and there's this other execution where I just sent B, and there's this other execution where I just sent C and B, C, and so on. So the power set, and then for each of these, you have to take the factorial,
Right.
because they could be delivered in any order. So you don't want to explore those things. It's subtle even in a simple, relatively simple protocol. And then you consider the protocols like Paxos who have infinitely long runs. Infinitely long runs where every step of the run has factorial times power set. Don't make me do the math. It's hard. So yeah, that will be you're reasoning in the right way. It's completely intractable. You can't do that. You have to figure something else. All right, where was it? Dependency, blah, 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 total order. Right. So it's going to turn out, we're going to spend a bunch of time in this class, that all of the strongly consistent replication protocols that we're going to study are going to be strongly consistent by establishing a total order over operations. But as we're going to see, and that's quite interesting, all of the replication protocols we'll study will establish that total order via different mechanisms. So they always get a total order, but they do it in different ways, and that's kind of what explains the differences between the mechanisms. And before we get into primary backup, which is the first replication protocol we're going to study, I want to say a word about this term strongly consistent that I've been talking about. I'm going to say this right today. No, I'm not. A replicated storage system is strongly consistent. This is a colloquial definition, but it's the definition we're going to use. I'm not going to be more specific than this. Strongly consistent if an outside observer cannot tell that it is replicated. Any externally visible evidence of replication I'm going to call, is a, or any externally visible witness, sometimes we'll call it evidence of replication or witness of distribution. Any evidence of replication is an anomaly with respect to strong consistency. Okay? So anytime I draw a picture in which a client sees evidence that the system is replicated, that means the system is not strongly consistent. Any replicated system in which no client can ever obtain evidence or a witness of the system being replicated is strongly consistent. Now, what the hell am I talking about? Like, what would a witness of replication look like? Now, harken back to some of the sort of conflicts that we reasoned about earlier today and in Lindsay's lecture.
What is it? WRT with respect to?
What do you think? So let's say, I don't just have one database. I have like 3
consistent
databases. And I have a client, maybe more than one client, interacting with these databases. What's some of the kooky shit that could happen that could make Carol, the client, say, hey, wait a minute. You told me this was just one database. I think it's actually running on a couple computers here. Because this would never have happened if it was just on one computer. Yeah.
Carol makes her read and get stale data.
Yeah, what do you mean by stale? Like, how does she know it's stale?
If she made like a write before, but it wasn't the read that she did immediately after wasn't the.
Exactly, and for this we have to pause it. Like, let's say for some reason Carol knows that there's nobody else in the system, because otherwise somebody could have come along. Let's say Carol knows she's the only one in the system, and she goes like this. She says, x equals 1, and then she goes, read x, and the database comes back and says x equals, well, I don't know, it's uninitialized. Carol's gonna be like, this is not a strongly consistent database. Right? Because if it were, I would have read what I read. What else? It's mostly going to be versions of that, right? But any other thoughts?
Network representation.
Let's say x is uninitialized, and Karen wants to write a value to x, but then decides to change her mind and writes it again, and the x values now two different values.
Oh, you mean she writes it to a different thing?
Yeah.
Yeah, and then she could do this, and then she could be like, read x like 10 times, and she's like, x is 1, x is 2, x is 1, x is 2. It's also true that if she did something like, you can imagine her, this could become really obvious if like she wrote her clock value to it. She's like, x equals, 335, right? And then later, she is like, x equals 340. And then she reads again, and then she sees it go back in time, or something like that. Well, it's like, well, it wouldn't go back in time if it was just on one database. That's crazy. So we could go on like this forever. The point is, there's lots of ways in which, if you're not careful, if you choose a reckless protocol for how you maintain consistency among the databases, a witness could come along and perceive the fact that the system is running. You all buy that?
What about the other user?
What about the other user? Well, then there's other things that could happen, right? Where
Yeah.
we could write conflicting values, x equals 1, x equals 2.
But all of those anomalies looks like they would be possible with one database and two users consuming it. Right. So is there a different type of anomaly?
Well, I mean, here's an anomaly. This is going to lead to an anomaly, right? Which is like, let's say that this guy thinks x equals 2, and this guy thinks x equals 1. I mean, only one of the two things. No, it couldn't, because then a client could come along, a third client could come along, and start saying, okay, there's no more writes allowed to the database. And they could read, and see the value oscillating, which is also something that wouldn't happen on a single site database. X wouldn't be 1, 2, 1, 2, 1, 2 in the absence of writes.
Okay.
Right? Okay.
Okay.
So now, with no further ado, let's talk about our first strongly consistent replication protocol. You have come across this probably in your studies. It's the simplest imaginable replication protocol, and it's called primary backup. Some extremely ahistorical people in our community still persist in calling this master-slave. Please don't say that in this class. This is a perfectly fine set of terms, primaries and backups. Okay? We have clients, and the essential idea behind primary backup is that we're going to elect a distinguished node called Peter the primary, who is playing the role of that single database that did everything right, that single database that we call root, right? And the way that P is going to establish a total order over operations is via arrival order, because why not? It's there. So P arbitrates the order in which the reads and writes happen based on the order in which the arrows happen to touch down on P's timeline. So P, so far, behaves just like Doris, the database, right? Except P has a squad of passive agents known as backups. And what the backups do is they follow a protocol. And the protocol essentially involves writing down in their disk whatever P tells them to write, and letting P know that they've done so in much the same way that reliable delivery works. Right? So client Clarissa says, hey, x equals 1, and the protocol unfolds in the following way. The primary stages that write on its own disk. It then forwards via broadcast. Could be reliable broadcast. Doesn't have to be. Via broadcast to backups 1 and backups 2. Backups 1 and backups 2 acknowledge. All right. When the write has been acknowledged by all the backups, we call that point on the primary's timeline the commit point. point at which the primary knows that in any future, even a future in which the primary crashes, that write is available on all the backups. In some sense, at exactly this point, the write has happened in a way that we can allow people to witness it, and witnessing it will never witness a violation of strong consistency. And then, of course, from the commit point, the primary can go ahead and acknowledge the client that the write is successful. Reads follow a similar pattern, except what? How would reads look different than writes? Yeah.
You don't have to broadcast a read to the backups because your backups are already consistent.
That's absolutely right. So reads could just look like this, right? I know that the primary, assuming it's up, has a statement here of up. Read x. Sure, x equals 1, pal. Right path? Read path. Yeah.
So does Peter delay delivery of the message until it's received acknowledgement from the backup?
Say again, the primary
Yeah.
is not going to write the data. This is subtle. It doesn't matter so much for the purpose of this class, but just so you asked, the primary is actually going to wait to write the data to its disk until the commit point.
Okay.
Because it's not going to want to expose it to a read early.
So it's like pending.
It's going to turn out that that's going to need to do that to rule out anomaly. Yeah.
So what would happen if while it was doing sending it to the backup and someone else asked to read the list? Suppose I say X is 1 and ask for X before it could submit the message.
Yeah, so in some sense, the interval between when the primary accepts the write and the commit point is a dead interval, right? During this interval, X's value is whatever it already was. There's nothing wrong with it. Let's even imagine another client coming along and saying, let's imagine that all the valued variables are initialized to 0, just to make our lives easier, right? Client comes along and it's perfectly fine to say X was 0 at this time. Because in fact, this is equivalent to an execution in which there was just good old Doris, right? And it was the exact same execution. This client started first, but their write got delayed. You see? So this client reads X, and yeah, of course X returns 0. And so anytime we're asking ourselves an execution that we just did in a distributed replication thing, is it or is it not a witness? Is it or is it not a violation of strong consistency? If you can draw the same picture on the diagram of a single database, and the same execution happens, then clearly it wasn't a violation of strong consistency. Right? Because there's non-determinism even in this world, because there's uncertainty about when different clients' messages are received. Does that make sense? That when I said, this is how I convinced myself that this was okay, is because it could happen on a single site database. So it must be okay. Right? Here's a question. Maybe this is a case for colored chalk. It's frequently the case that a smart engineer is developing something that looks like primary backup, and a light bulb goes over their head, and they're like, you know what? The primary is overloaded. The primary's doing all this work. Backups aren't doing that much work. I bet I could get a lot of extra read bandwidth by redirecting reads to the backups. Is that okay? Because, God, there's all these spare cycles hanging out here. You've got to be able to use it for something. I mean, we should have these things mined points, right? That's what we should do. But okay, is there anything we can do to correct this imbalance? Because in some sense, the primary is going to all work, which means this whole system of replicated computers is only going to go as fast as the primary. That's a drag. So what happens if, for example, so I write X equals 1. Then I read X. Well, I get back X equals 1. And then I read X again. And I get back X equals 0. My read just went back inside. See what happened? I read a backup who has made available the write before its commit point. Because if you wanted to reveal it later, you'd need another phase where you told the backups to reveal their stuff. This is getting too complicated, right? So I read a value that shouldn't have happened yet. And then I redirected the primary and read an old value. So I read the future, and then I read the past. And that was confusing. right? So TLDR, you can't read the backups. Yeah.
What would happen if the primary crashes before the commit point and the backup has to take over, it's already written over it?
Good. What would happen if the primary crashed before the commit point? Same thing would happen if Doris crashed before she got the read. That right didn't happen. And it's okay, because it's not like the client ever got an acknowledgement that the write happened.
Well,
Right? So in some sense, you're awaiting your acknowledgement. You send something, hey, do this and let me know when you're done. And I never hear from you. It didn't get done.
But it's already wrote it, like, at a point after it's already written. So like, suppose, primary sends something to B1 has written it to its.
No, you're absolutely right. So let's reason it through from first principles. It didn't happen, right? Because we didn't make it to the commit point. And so in order to look like this system, it has to have not happened, which means that whatever happens after a primary fails, which we haven't discussed yet, happens, we're going to need to make sure that it's as though that write never happened to the backup, right? And this is where primary backup gets dark. So do we have time to get into that today? We have like 5 minutes. Let's just start touching on the subject. We sort of have, right? If the primary were to go down, and we suspect it will, or we wouldn't have bothered doing stuff on other machines. Obviously, what do we want to happen in the primary? Intuitively. Yeah, well, we want one of the backups to step the F up, right? And become the primary. And we want the other backup to keep being the, we don't want there to be 2 primaries, that would be bad. But we want there to be not 0 primaries, that would also be bad. So we need some way to somehow get, I don't know, consensus to decide who's the new president. And not just that, but make sure that whoever's the new president looks through their log of committed things and knows which of the things that were halfway done, and then make the decision that I brought up earlier in class. Like, when something's halfway done by a process that crashed, you have 2 choices. You roll it back or you roll it forward. So typically in primary backup, what's going to happen is you roll back the incomplete things, take them out of the sequence. That takes quite a bit of subtlety, and it needs to be done atomically. And that's why, for the time being, the way I want you to think about this is, there is a configuration server, Charlemagne, right? And that configuration server's job is just to know everybody who's out there. So that configuration server might say, in view 1, there's a primary, who's the primary, and there's a backup 1, who's the backup, and there's a backup 2, who's the backup. That's the view of the world. And maybe at some point in the protocol, they've told everybody, hey, here's the view of the world. Why? Well, because the primary needs to know who the backups are. The client needs to know who the primary is, right? So it's important for everybody to have this like view of the world. And this view of the world is going to change over time because machines are going to crash. And if all that happens is machines crash, then this view will just get smaller over time. That won't do. We need to be able to add machines, right? If the primary crashes, okay, now this guy's the primary and this is backup, but probably we want a backup 3, right? So the idea is we want to move atomically between configurations. We want some way to say, okay, that was the one view. And in the event that the primary were to crash, we want to atomically move to some new view called view 2, in which the server previously called B1 is now the primary. And the server previously called B2 remains as a backup. And we want to remain in that view for a very short time because we also want to add a new backup probably to get back to our level of resiliency. And then we'll be in view number 3, in which the server previously known as backup 1 is the primary, the server previously known as backup 2 is a backup, and the server now known as backup 3 is also a backup. And we need to make these transitions in a way that everybody sees them, and everybody does them all or nothing. The mechanism we're going to use to implement Charlemagne, the configuration server, is going to be consensus. And this is going to be a cluster of machines that are cooperating together to provide this consistent view. And obviously the name of the game is you want to be able to react to the loss of the machine very quickly, right? But not too quickly, because it's impossible to tell loss from delay in the distributed system. And so if you tune this thing up too aggressively, you're going to get into a position in which you like kick out the primary because you think he's dead, and then you have to switch again because he's back, and then you kick him out again, and he's back again, and so on. Where if you tune them not aggressively enough, you can have the system be unavailable for a long period of time in the event that the primary goes down. Okay? All right, well on Monday,